The alert started at 3:17 p.m. API error rate spike. Within seconds, the graph shot upward. 5%, 10%, 20%. Requests were still flowing through the load balancer, but something downstream was failing badly. At the same moment, Slack notifications appeared from our deployment pipeline. Production deployment completed successfully. That message should have been reassuring. Instead, it made the situation worse because the error spike started immediately after the deployment finished. Someone typed the question everyone was already thinking. Did we just ship something broken? Our platform ran on AWS using Kubernetes through EKS. The main API handled authentication, billing, and account management. Around 120 pods served traffic behind an application load balancer. Traffic averaged roughly 4,000 requests per second during peak hours. Each service ran inside a Kubernetes deployment configured for rolling updates. New container versions replaced old pods gradually while maintaining availability. The deployment configuration used the default strategy. One new pod started while one old pod terminated. Health checks verified readiness before the pod entered the load balancer. If a deployment introduced errors, Kubernetes allowed rolling back. CI pipelines built container images through GitHub Actions and pushed them to ECR. Deployments were triggered automatically through Argo CD. Deployments were triggered once a new image tag appeared in the repository. Monitoring included Prometheus, Grafana, and Datadog. Normally, deployments were routine events that finished without anyone noticing. Within minutes of the deployment finishing, the API error rate reached nearly 30%. Login requests failed intermittently. Some users received internal server errors. Others experienced extremely slow responses. But the strange part was that the errors were inconsistent. Some requests worked perfectly, others failed instantly. The load balancer health check still showed healthy targets. Pod CPU usage looked normal. Memory consumption was stable. At first glance, the infrastructure appeared healthy, yet the error graph continued climbing. Customer support began reporting that users could not log into their accounts reliably. The product team joined the incident channel. That was the moment we noticed something odd. The deployment had already finished, and Kubernetes reported it as successful. The first step was checking pod logs. Several pods showed stack traces related to a missing configuration value, but other pods were operating normally. That inconsistency suggested that only part of the deployment was affected. We inspected the running pods. Half of them were running the new image version. The other half were still running the previous version. That was normal during a rolling update, but then someone noticed something strange. The new pods were restarting frequently. Every time a new pod started, Kubernetes terminated one of the old pods, but the new pods were failing shortly after startup. The container process crashed within seconds. Kubernetes restarted them automatically. Each restart triggered another attempt. But the system had already terminated some of the stable pods. Over time, more healthy pods were replaced with broken ones. The root cause was a configuration mismatch between the application code and the Kubernetes deployment manifest. The new version introduced a required environment variable for authentication. The container expected that variable during startup. However, the deployment manifest had not been updated to include the new variable. When new pods started, they attempted to read it. Because it was missing, the application crashed immediately. The readiness probe never succeeded, but the pod still started briefly. Kubernetes treated the pod as part of the rollout. Meanwhile, the rollout strategy continued replacing older, healthy pods. Because the restart loop was gradual, the deployment controller believed progress was being made. No automatic rollback occurred. The fastest way to stop the failure was pausing the deployment. We executed a command to halt the rollout immediately. Next, we initiated a manual rollback to the previous container image. Kubernetes immediately began restoring the older pods. Within a few minutes, the number of healthy instances increased and error rates started falling. The service stabilized. After restoring stability, we fixed the configuration issue by adding the missing environment variable to the manifest. A new build was deployed later. Total incident duration lasted about 22 minutes from the first alert until completion. Post-mortem reflection. What actually failed was not the rolling update itself, but the assumptions in our deployment pipeline. The deployment manifest was in a separate repository. Because the pipeline was automatic, The configuration mismatch reached production. Detection was delayed. Infrastructure monitoring showed healthy nodes, which initially masked the application-level failure. Engineering lessons. Application changes that introduce new dependencies should fail fast in staging environments first. Deployment pipelines should validate environment variables and required configuration during container startup. Rolling updates should include stricter readiness checks. Automatic rollback mechanisms should trigger when error rates spike. Sometimes the most dangerous deployments aren't the ones that crash instantly, but the ones that quietly replace healthy systems one pod at a time.